secant method is very, in fact, it's the extension of Newton-Raphson method. So here, sometimes, it's hard to compute the derivative, especially if the function is not known. Okay, if I don't know the function, how do we compute the derivative? So, well, we can do it numerically. So the idea is to just replace f prime x by fxn minus fxn minus 1 divided by xn minus. So this is the 1 divided by f prime x xn. Okay, I'm estimating using the last two values. Okay, and you can see from here this xn and this xn, this xn minus 1 and this xn, and we get this slope. It's not the exact slope here at xn here, but it's okay. I mean, we are doing numerical only, so this is an approximate slope. Okay, so secant method is derived from Newton-Raphson, but using numerical values, and it's useful when we don't know the function. Okay, now let's apply this to this again exponential. And you can see the secant method is equally fast in convergence. It is converging quite fast in 5-6 steps, and but it fails for cube root of x. It is not, in fact, the behavior is a bit different. It is not going to infinity, but is basically oscillating between 4 values. Okay. It just goes back and forth in 4 values. Okay. Now, the last method which I'm going to describe is the relaxation method. So, this function is slightly different. Often we come across a problem where we need to find solution of this equation, fx equal to x. For example, in condensed matter physics, you find x equal to 10x. Okay, I think it's for band value. I mean, for getting the band structures, you get. So we get some things like this. One function I'm going to show you that shows chaos. Okay, very simple function which shows chaos. Okay, so this is different than finding root. Huh? So if you want to write in terms of root, then it is fx minus x equal to 0. I'm finding root of this function, but it is stated as finding the solution of this equation, fx equal to x. Okay, now in fact what we do is it's a relaxation method or iterative method. It's a iterative method. So you given xn, you compute xn plus 1 by just saying fxn equal to xn plus 1. Okay, so we compute like that. Now, so this function is, in fact, it is ax1 minus x. I did it for 2.5. This x equal to 2. A is 2.5. Okay, it's a quadratic function. It is 0 for both x equal to 0 and x equal to 1. Now let's iterate it. Let's follow this. So if you start from this value x0, so there are 2 roots. No, the one root is here and one root is here. You start from this value, then my function fx0 is here, and so what is x1 now? So this line is y equal to x line. This is a 45-degree line. So we just take this, you make a horizontal line from fx0, you reach here, and that is x1. This is x1. Okay. So basically, this is x1, and how do I get that one? You just push it to the horizontal line, and this is the box. It is in fact is a square. Okay, so that is x1, and once you get x1, then you find function here, value of the function at x1, which is going to give x2. Okay, the values are too close, but you can see that it is iterating. In fact, my function is here. I go here, I get here, then from here again I come here like this, keep going down. So it turns out that this point, the point near, the one point is x equal to 0, other point is here. This point will converge. My iteration will converge near this point. Okay, this point is in fact it's called a stable fixed point. Fixed point. And in fact the solution of this equation is called fixed point. X star equal to fx star. That's the solution, no? And so this x star is called fixed point. If you are at x star, then it won't move. It will remain there. That's fixed point. What about the x equal to 0 point? If you start from x naught, then do I go close to 0 or I go away from close to 0? It turns out that if I start from x naught, then I just do the same step. I extend the horizontal line and I reach here and x1 is here. So I'm going away from the root, right? I'm going away. And from x1, I go to x2, which is going away. So this x equal to 0 is an unstable fixed point. It's an unstable fixed point. Okay, so we can get both sorts of fixed points. So convergence, in fact, if I apply this idea, xn plus 1 equal to fxn, I'm not going to get to the value, to the fixed point. So what should I do for this solution, to get to this solution, unstable fixed point? So idea is, in fact, let's do a convergence test first, then I will tell you how to get there. So convergence test is very simple. So remember I had xn plus 1 equal to fxn. So my solution is x star. So I just say x star minus xn plus 1 equal to x star minus fxn. So I do Taylor expansion. X star minus fx star minus x star minus xn f prime x star. Okay, Taylor series fx. Okay, we are doing it right. Fx plus fx equal to fa plus fx minus a. So it's the other way around. Xn minus x star. Okay, so that is fxn. So what is fx star, which is same as x star? That's the definition of the fixed point. So this cancels, and I get here xn minus x star, which is the error epsilon n. Okay, is minus. Okay, so minus is plus epsilon n f prime x star, and this is epsilon n plus 1. Okay, now I want epsilon n plus 1 to be less than epsilon n. Correct? Modulus wise, mod error. It could be changing sign, but I want the mod to be less than 1. So I want epsilon n plus 1 divided by epsilon n mod to be less than 1. Implies f prime x star must be less than 1. Okay, so that's the condition. So I'm just going to make some space here to the left. So my a x, let's use green color, 1 minus x, this is my function fx. So my two of the solution, well, at x equal to 0, what is the slope at x equal to 0? F prime at x f prime at 0. So it is ax minus ax squared. So x squared will be 2ax, which is 0. So the f prime 0 is a. Now for a greater than 1, we can see that slope will be greater than 1. So my a, in fact, for that example was 2.5. So that means my x star equal to 0 is an unstable fixed point. It is not going to converge. Okay, so that's the reason. If you just work out for other solution is, you can just work it out. Other solution is x equal to 1 minus 1 by a. Okay, and this solution, if we just, well, we can just do it right now. F prime at this other fixed point. So, okay, I can give you the answer. Okay, for a between 1 to 3, if you have a between 1 and 3, then this fixed point is stable. The slope will be less than 1. Okay, you can just work it out. For a less than 3 and greater than 1, this is that 1 minus 1 by a is a stable fixed point. Now, when a exceeds 3, then this fixed point also becomes unstable. So both become unstable. 0 becomes unstable, and this will also become unstable. And in fact, this system shows period doubling. Okay. If you look at Wikipedia, you will find this in terms of logistic map or quadratic map. This also has the name quadratic map. And this system, for beyond something like, I believe, 3.5 or so, it shows chaos. So if you start with any value of x, it will keep jumping up and down. It will just go everywhere. Okay, it won't converge. Period doubling, it doesn't converge to a fixed point, but it goes A, B, A, B, it does like that. A, B, A, B, A, B, A, B. You'll find that it does like that. You can easily do this in your computer. Huh? I mean, this is straightforward. This is how we test the convergence. Convergence condition is this. Your fixed point, your iteration will converge to a fixed point if the derivative modulus of that is less than 1. Okay. Now let's solve it for this particular example. So it is between 1 and 3. So 0 is unstable by mathematics, and that 1 minus 1 by a, which is, you can figure it out, this some value. That is, this one is stable. And indeed, this is the value. This is the one. This is this value. Okay. Now, okay. So this will converge. Xn plus 1. This will converge. How do I get this fixed point? There's a tricky part. How do you get this fixed point? Well, it's easy in numerical stuff. So remember, so here, if I start from x0, I go like that, right? I'm going away. But if you go back in time, then what happens? So if forward in time, I start with x0, I go to x1, I go to x2. Back in time will be, I go from x2 to x1 to x0 like that. If you go back in time. And what is going back in time? Is straightforward, very easy. So we have xn plus 1 if fxn. So I need to go back in time. So what do I do? Xn equal to f inverse xn plus 1. Right? Inverse function. You have to make sure that inverse exists. Okay. There may be two solutions, but you have to choose the one. In fact, this one will have quadratic equations, so it will have two solutions, but choose the correct one. Okay, by seeing the property of the function. And so we just run this inverse. So I start from xn plus 1. I just choose any value, in fact, some value. Then I go back in time, just do f inverse, and you'll reach there. And that is what is done here. I start with 0.2, I substitute here, and I do inverse function of this, f inverse. So I get here. Then I do another inverse, I come here, and I reach close to 0. If you just iterate for long enough, I'll get to 0. Okay. In fact, this is 0. Okay. So that's how we converge. So Python's root finder. So if you're lazy and you don't want to write your own code, there are in fact 4 functions available with Python. And usage of the function I'm showing you here. So it's part of optimize package, part of SciPy, module. Within SciPy, there's optimize library module. Okay. So we define lambda function G, okay, which is x squared minus 1. X squared minus 1. So idea is to optimize dot Brent Q. So the G function G and left bracket and right bracket. It could have more than one value. No, it has in fact 2 values, minus 1 and plus 1. So I need to specify. I want the root in which regime. So 0.5 to 1.5. So this will give us 1.0 is my value. Okay. Now answer it gives you is 0.99999. So it basically is 1.0. Okay. Is part of optimization module. Now, if I put my bracket is minus 1.5 to minus 0.5, then I'll get minus 1 is the solution. That's one. Okay. You can have more complex function like this sine pi x minus x. Okay. So it has solution. In fact, is 2 solutions, right? Sine pi x will be like this. X. Okay. It becomes 0 at x equal to 0 and x equal to 1. And x equal to y equal to x is this. So if I choose my interval as minus 0.1 to 0.1, then I'm going to get 0. And if I choose my interval from 0.5 midpoint to 1, then I get this, which is this one. All right, so we can use this function Brent Q.